From the Kingdom of Saudi Arabia, gathered a group of undergraduate students under the banner of King Abdulaziz University. We are the Drone and Robotics Aziz Group. This video is a review of our project's technical design and flight readiness. Our development team consists of 15 members divided into 3 sub-teams: Operation, Airdrop System, and Imaging ODLC teams. And this is our competition team that will carry out the mission. Operating in synergy, the entire team collaborates with the shared goal of engineering a high-performance system with practical real-world applications. Our mission is segmented into 4 primary areas: timeline, operator, airdrop, and operational excellence. We have optimized our setup and teardown processes, reducing setup time to under 10 minutes and ensuring our UAV can travel 15 miles within the 30 minutes mission time, while not exceeding the weight limit. Our lightweight design and fast cruise speed of 52 feet per second enhance efficiency, avoiding the need for any timeouts. To maximize our points in the operator segment, we limit ourselves to 2 operators, a safety pilot and a GCS operator. Our UAV equipped with RTK GPS to ensure ultra-precise waypoint navigation and maintain strict adherence to mission boundaries. Additionally, the system features obstacle avoidance and can accurately identify targets. The airdrop, the most crucial part of our score, demanding precise payload delivery and object classification. Our UAV excels in these tasks, enhanced by advanced sensing and GPS technology for pinpoint accuracy. Additionally, it features a high-quality camera mounted on a gimbal for stable, clear imaging, and is powered by a Jetson Orin computer, ensuring swift data processing and real-time decision-making. Operational excellence is paramount. We maintain professionalism, efficient communication, and quick response to failures. Our adherence to safety protocols ensures smooth operations, aiming to exceed competition standards. We utilize a heavy-lift hexacopter with a monocoque carbon fiber airframe that is both lightweight and waterproof. Powered by 6 motors and 60 ampere ESCs, it produces a total thrust of 115 pounds, enhancing lift and agility. The propulsion is supported by 4 25 amp-hour LiPo batteries, offering a substantial 42-minute flight capacity. Our airdrop system reliably delivers 5 payloads with pinpoint accuracy. Navigation is managed by the Cube Orange flight controller, ensuring dependable autonomous operation. Safety is bolstered by a LiDAR-based obstacle avoidance system, and an RTK GPS provides centimeter-level positioning accuracy. For communications, we use HearLink for RC control and an RFD900 for robust telemetry. Our imaging system features a high-quality camera and Jetson Orin that are both stabilized on a gimbal to reduce vibration and enhance temperature control. Mission parameters are finely tuned using Mission Planner software, ensuring the UAS operates with surgical precision on the field. Selecting the right camera for our UAS was critical. We selected the Raspberry Pi high-quality camera paired with a suitable lens, known for its seamless integration with the Jetson Orin Nano. This combination provides the flexibility our mission demands. To maintain high-quality imaging, we have optimized the camera settings to suit the mission environment. By fine-tuning the exposure time and frame rate via our software interface, we effectively minimize motion blur, ensuring all images captured are sharp and clear. The addition of a 3-axis gimbal stabilizes the camera platform, virtually eliminating vibrations that can degrade image quality. Our choice of a 16mm lens offers the ideal balance between field of view and magnification, which minimizes the need for in-flight adjustments and allows us to concentrate on the mission objectives with greater precision. Our analysis shows that this camera setup excels in identifying ground objects from an altitude of 23 meters. This capability surpasses our mission's requirements for object resolution. To establish the framework for executing the mission, each captured frame will be processed using YOLO to detect objects. Following detection, the objects will undergo classification based on 3 attributes: letter color, and shape color. This structured approach ensures accurate and efficient analysis of each frame. Then we applied K-means clustering to our image, resulting in an image with a number of segmented areas where pixels share similarities in color intensity and spatial distribution. This segmentation enabled us to isolate and identify various image elements such as letters, digits, and shapes. Furthermore, we isolated K-means segments that represent letters and digits by creating a binary mask to separate them from their backgrounds. This masking process makes important details stand out while removing unnecessary background clutter. And to handle images taken from different orientations, we have an algorithm that detects the orientation of the text and rotates it accordingly. This ensures that the classification model always sees the text in the correct upright position. For localization, we've developed a two-step method to guide our drone. First, we calculate the object's direction and distance. Then we use these calculations to navigate the drone swiftly and accurately towards the target. Now let's examine the impact of using a gimbal on our UAV's image quality and the overall performance of our object detection system. The images captured with the gimbal show significantly improved stability and clarity, with a substantial reduction in motion blur. The average resolution of objects in these gimbal-stabilized images meets the rigorous quality standards required for precise analysis, ensuring detailed and actionable data. Our comprehensive testing verifies that with this enhanced imaging setup, our system effectively recognizes and categorizes over 90% of the specified targets. This high success rate underlines the effectiveness of our imaging system when equipped with a gimbal. In our quest for the most efficient payload delivery system, we explored several innovative solutions in the following alternatives: motors and roller, spring brake, and the parachute mechanisms. The motors and roller mechanism features 5 motors and 5 servo motors that are mounted on a 3D printed base, which lock the roller mechanism. When activated, the motors initiate the roller's movement, causing a controlled descent of the object. While the spring brake mechanism uses a complex assembly of gears, a spring, and a servo motor to control the descent of the payload. Although effective in reducing drop speed by compressing a spring to slow the payload as it descends, its overall weight exceeds our operational limits, impacting our UAV's flight efficiency. The parachute mechanism utilizes a nylon parachute stored in a canister, deployed via a servo-controlled trapdoor. The parachute ensures the payload's safe landing by cushioning its descent. This method is highly dependent on wind conditions, which leads to variable accuracy. All these designs showcased our team's commitment to innovation and thorough testing. While they provided valuable insight, the following criteria determines the chosen mechanism. And after thorough evaluation, we chose the motor or roller mechanism due to its reliability and its ability to achieve an object landing time of 8 seconds with precise landing within the target area. With our chosen mechanism, we can ensure precise and smooth descent by setting the fishing line slightly shorter by 2 meters to eliminate the need for any cutting mechanism. And for reliable operation, an Arduino Uno microcontroller manages the system, communicating with the Jetson Orin Nano device via serial communication. During the testing phase, we started testing with a diameter of 1.1 inches, and after several calculations, we found that a diameter of 2.3 inches was the best option. And we used the following equations to calculate the descent time. Experimentally, when the tests were done several times, the time was equal to 8 seconds. The experimental results show that this system is capable of completing the drop mission within the criteria. Out of 35 drop attempts, 34 were successfully completed within a precise range of 20 feet. The average time for each drop is just 8 seconds. This gives us an impressive airdrop success rate of 97%, showcasing the effectiveness of our UAV's delivery capabilities. Our UAV's communication system is structured around 3 key components: the ground control station, the safety pilot, and the hexacopter. We utilize the RFD 900 modem for telemetry and control at 900 MHz with frequency hopping spread spectrum to avoid interference, achieving an impressive outdoor range of 24 miles. Additionally, the HearLink system transmits RC control and telemetry over 2.4 GHz with a 12-mile range, providing real-time data to the safety pilot. In extensive testing, our communication system maintained a stable high-throughput connection, achieving 400 kilobits per second